Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing sediment data, specifically entering the sediment data file data for initial conditions and transport parameters. All right, what I have on the screen here is my HEC RAS, and what I'm talking about is if I go click on the sediment data, which I can also access via Edit Sediment Data, I'm going to be talking about this first tab right here. This is how I add and create and update and rename and delete sediment files. So there's three tabs in this interface. This particular lesson is going to be about the first one, initial conditions and transport parameters. But there are two other tabs right here as well. Okay. So once this sediment data is saved and created, then we can use it in a computation. So if I go up to run and then quasi unsteady analysis, that sediment data can be selected from this drop down right here. Or if I happen to be using the sediment data file for an unsteady flow simulation, that would be click on the sediment checkbox, and then that would be selectable from this drop down right here. Okay, let me go ahead and close that. This is the web page that introduces the topic of creating a sediment file. And if I expand the window wide enough, I get this side menu that pops up here. If I click on the next menu item down here, I'm in the HEC RAS 1D sediment transport document online. Initial conditions and transport parameters. So this page right here is going to be the page I'm going to leave a link to in the description of the video if you'd like to follow along. And what we're going to be talking about is going to be covered in these subpages listed here in the menu: transport function, sorting method, fall velocity methods, and so on. All right, let's go ahead and go back to HEC RAS now. What you see is a river reach with station data, cross-section data at river station 5,000 all the way down to river station 0 at a 1,000-foot interval. And we're going to be using the cross-section data from the geometric data editor in this lesson when we see a similar display. All right, so let's go ahead and get that sediment data file started. Like I mentioned earlier, we're going to go up to Edit and then Sediment Data. Or again, you can click on this button up here in the Toolbars menu, which reads View/Enter Sediment Boundary Condition. Looks like a SED with a little cross section. Boom. So let's get started by just creating a new file. I'm going to go File, New Sediment Data, and then I'm just going to call this, I already have a test. Let's go with test2. Okay. And then if I actually move this down, we have test2 listed as the current sediment file. This is the title, and then this is the actual path to that file. All right, so let's work on our test2 sediment file here. With the initial conditions and transport parameters tab selected, first we want to select the river and the reach. So this means that we can only edit the sediment data for one river reach at a time. Click the river, click the reach, and we're good there. Next up is the transport function. That's this drop down right here. As you notice, we have a number of different transport functions available to us: Akers-White, England-Hansen, Larson-Copeland, and so on. I'm not going to read them all, but you can read about them all you want in the user's manual. So let me make this wider again to see the side menu. If I click this transport function page and then scroll down just a little bit, there's links to all of these different methods. So if I click on one of these methods, such as the first one, we're getting some of the background and theory with the equations and so on. So go ahead and use the transport function that works best for your particular model. And if you're not sure which one works best, then you can ask somebody, or you can go through the research and some of the documentation and figure out which one would work best based on your particular model. All right, the next parameter down here that we need to specify is the sorting method. Now there's a number of different options here: Thomas, Active, and Copeland. And it looks like Thomas Acklin, Active, and Copeland a second time. I'm not sure why that's happening. That wasn't the case earlier. Well, anyway, I think there's only three: Thomas, Active, and Copeland. I tell you, this software. The sorting method is sometimes called a mixing method or an armoring method. Sorting methods are used to track bed gradation, which HEC RAS uses to compute grain class specific transport capacities, such as armoring. Armoring is where a coarser layer of sediment lays on top of the natural bed sediment and protects it from erosion. So it sort of serves as a coat of armor and reduces the amount of erosion. This first method, Thomas, right here, this is the method that has the most armoring. Thomas is a three-layer model that includes armoring. This method has the most armoring and hence the least erosion. Now, the next model down here, I'm going to talk about Copeland next. This is based on the Thomas method, but it's used in sand bed rivers, and it has a little bit less armoring than the Thomas method and hence a little bit more erosion. The last method is the active layer method. This is a two-layer model. It's simpler than the Copeland and the Thomas method, and it's easier to use and also easier to interpret results according to the user's manual. The user's manual also shows a picture, a colored picture actually of armoring. So if I click on sorting method and then I click on the top, oh, here it is. So if someone took a shovel to the bottom of the riverbed, then they would see the armoring right here, the larger rocks that reduce the erosion. And then down here is more of the natural gradation of the soil of the riverbed. Okay, the user manual makes a few other mentions. So, for instance, if your transport method happens to be the Wilcock-Crowell method, you want to also select active layer here for your sorting method, things like that. Next up is the fall velocity method, and we have a number of different methods to choose from here as well. Fall velocity is also known as settling velocity, and it refers to the speed at which a sediment particle descends through water under the influence of gravity. So go ahead and select the appropriate fall velocity method there. There's also a separate page for fall velocities listed in the user's manual. All right, after those are selected, I want to divert your attention down to this table down below here. So based on the river and the reach that we selected, we have a table listing all the cross sections in that river reach from 5,000 down to 0. And that represents one row per cross section with the listed invert values of 40 down to 35. All right, the columns in this table are river, reach, river station, and invert elevation. I think that's all pretty straightforward. Next, we have max depth and min elevation. So these two sort of work together. The user's only going to either type in max depth exclusive or min elevation, but not both. Max depth is more likely to be the case. This is the maximum depth of erodible material at this cross section. So if the invert is 40 feet, but there's another 3 feet of erodible material, the user would type in 3. Max depth, I believe, is used when the user is not quite as sure of what that depth is. It's more of an estimation. Min elevation is when the user is sure of the actual minimum elevation so that the erodible material can't erode past that elevation. So if it really was 3 right here, the min elevation would be 37 because that's the elevation 3 feet below the invert of 40. So I'm going to go ahead and change it back to 3 though. That's what those two columns are. Then left station and right station, these two also sort of have a similar idea, and that is the cross section station that erodible material is located in. So if, for instance, it was 3 feet of erodible depth for the entire width of this river station cross section, then I would type in station 0 for the left and 350 for the right. That'd be 0 and 350. And then if I mouse off that row and then mouse back on, you now see this dashed line here that the legend tells us is the potential erosion. So the solid black line is the ground elevation. And then this dashed line is actually 3 feet below it based on our numbers here and the left and right stationing data. Now, if I change the stationing data to something else, like how about this point right here? This is 50, and then this is 300. So if I change the left to 50 and then the right to 300, and then for it to update, you have to kind of click off and click back on, but it does update. Now there's going to be no erosion for the first 50 feet and last 50 feet of this cross-section stationing. Instead of typing in numbers into the table here, you could very easily use these buttons right here, LB and RB. So if I wanted to move the left bank over to the left, I would use this button, and then to the right, I would use that button. So I can move that around. Same thing with the right sediment bed station. Sediment bed station is what it's called, and that's represented by these yellow dots. Also, what's happening is the table is also updating. So right now it's just the channel bottom, the 50 feet of width from 150 to 200. But what's most common is using the bank station for the sediment bed station as well. So the yellow dots are at the same location as the red dots. And I can use the arrows, but if I wanted to set that for every single cross section, This is apparently common enough of a situation where somebody would want to actually develop a button for that. And that's what this button is right here. Use banks for movable bed down here at the bottom. So if I click that, then boom, automatically the left station for all cross sections and right station for all cross sections has been updated. Now, what you're seeing here is the cross section plot tab. And there's also a profile plot tab right here, which is not complete because I need to specify either the max depth or the min elevation. So let's go ahead and keep it on this profile plot. And then I'm going to just type in an erodible depth of 3 feet for all the cross sections in this reach. Okay, so there it is. The ground elevation again is the solid black line, and then the potential erosion is this dashed black line. This side view or this what you call profile plot is also helpful. For instance, if you had some variation. So say for instance, I'm going to change some numbers here, right? So now I've changed some of the max depth values and you can see that there's starts with 3 feet of erodible material up at River Station 5,000, but only 1 foot of erodible material at the bottom of the reach at River Station 0. All right, the last column in this table is the bed gradation. And if I click the drop down, I don't have anything to select, even though there's looks like multiple blank values there. What I need to do first is define a bed gradation so then I can select it from this drop down. So the HEC RAS is using sort of a template format, so you don't have to manually enter bed gradation every time. What you do is define a bed gradation and then select it from this list. So let's go ahead and do that. There's a button right here that says define/edit bed gradations. Each cross-section requires initial bed gradations. User define the sediment in the database that's associated with the appropriate cross-section. And what we have here are 3 tabs: gradation data, local cohesive data, and 2D polygon sediment. For gradation data, this is what we're going to be talking about the most here. Sort of a grain size distribution where you've got the size of the particle and then the percent finer or grain class percentage. Let me go ahead and create a new bed gradation here. So to manage the bed gradations, we want to start by clicking the new bed gradation button here. These buttons from left to right is new, rename, delete, and copy. So I'm going to go ahead and just click new. And then I'm going to name this first bed gradation grad 3500 to 5000. Okay, then I'll click OK. And now what I need to do is enter the percent finer values in this column here. Or if I know the grain class percentage, I'd select this radio button down here, and then it switches over to a range of sizes and then the percentage in the class. So I'm going to go ahead and do a quick example of both. Here's percent finer. Okay, so I entered the data from the user's manual. This is the example that they used. And what you're seeing here is that there is 0% of the sediment sample of the bed gradation that is smaller than 0.25 millimeters, but all of it is smaller than 256 millimeters. And then you can see the distribution right there. If you wanted to see what this distribution looks like using the grain class percentage, you can actually just click on this button right here and it'll convert. So if I click on that, boom, now we see the percentage of that bed gradation by mass in each of these ranges of soil sizes. So that's gradation from 3,500 to 5,000. I'm just making that up as a name. But what I'm going to do is if I wanted to rename it, I'd click that, delete or copy. I'm going to go ahead and just create a brand new gradation. I'm going to call it gradation from 500 to 1,500. And I'm referring to the river station here. So we'll get on that just a moment and then click OK. All right, so I have my 2 different gradations. I still need to edit this second gradation here. And I'm going to demonstrate the grain class percentage and just pretend that it's an equal 25% for the following 4 grain class sizes. These values do not have to add up to 100. They're just normalized, so it's on a percentage basis. This, what you're seeing on the screen here of 425s would be the exact same data as 4 1s or 4 2s or whatever. So if I wanted to convert that, what that would look like is 1, 2, 3, 4. Again, it doesn't need to add up to 100% apparently. So far, I've defined these 2 different gradations, but if I wanted to define more all at the same time, I can click this button here that says enter multiple gradations in a table. And when I do that, 5 sets, yeah, so I can change the number of sets, give it a name, and then in the next up to 20 rows here, define the data and that would be for percent finer, I believe. So you go ahead and do that. The data down here, I'll talk about in just a moment. All right, once those gradations are set up and saved, then we can go ahead and define them in this table here. Okay, it looks like I did not save the second gradation. Let me edit, define. Oh, okay, guess it went away. Let me go ahead and save that this time. I'll just go ahead and make a copy of this one. Gradation from 500 to 1500 River Station. Okay, let me just delete that data. And then 1, 2, 3, and 4. If I click OK, I think that saves. Okay, there it is. Good. All right, so let's see. River Station 5000 and 4000 would both take on this value. River Station 1000 would take on this second gradation value. And then there's a button down here for interpolate gradations. So for instance, if you don't have the actual gradation at a specific river station, but you have it upstream and downstream, and you want to assume that there's an interpolation, not a problem. Just go ahead and click on interpolate. And then these two are interpolated. And then if it's outside the range of gradation data, what it's going to do is just copy the closest, like the minimum here. So at River Station 0, it's just using the exact same gradation as River Station 1000. But then River Stations 2000 and 3000, those gradations are interpolated from the gradation used at 1000 and 4000. All right, so I told you I was going to mention these last few fields down here. This refers to the cohesive properties of the gradation. So it's this rows 21 through 25. This is if you're editing the data in mass, in bulk, multiple sets at a time. But where this data can be found at an individual gradation level is hold on, if I click here, yeah, it's the second tab here, local cohesive data. So what I'm doing is I'm editing the local cohesive data for gradation 3500 to 5000. Here are the parameter values: shear threshold, erosion rate, mass erosion threshold, and mass erosion rate. And then type the values in these fields right here. And if it's dormant, you can just leave it unchecked. But if it's actually active, you can check this checkbox right here. So because of this cohesive data, it's possible that you'll have multiple gradations that have the exact same data in this table right here, but they may have different cohesive properties. So I'm going to go ahead and close that finally. There's also a third tab here for 2D polygon sediment data. I have not covered anything related to 2D yet, so this will have to wait. In a future lesson, I'll talk about that one. So this is our sediment data. We've got it covered for our entire reach. I'm going to go ahead and go File, Save Sediment Data, and then go ahead and close. All right, well, that is it for this lesson. What we did was learn how to create a sediment file by going File, New Sediment Data, and then using the initial conditions and transport parameters, we assign the data on this table from the drop downs to the tables as well as the bed gradation.